Is it going to record? Yeah, it's going to record this time. Okay then. No, don't want that one. Want that one. For those of you who are late, please be punctual next time. Right, okay, phase test deadlines. Because things are going slower than expected, I have had to push back the phase test deadlines. So phase test, which was lecture 8, is now going to be on the 19th, and the other phase test is going to be on the 7th. Remember that there are part phase tests all the way through the other lectures, so be here on time. Okay, this means that one of the phase tests is in January, which sucks. But there we are. I would rather you passed than I just failed everyone, or some people. Okay, let's go through the week in review. What we learnt last week, what you should definitely know, and if you don't know it, you should be yelling at me. Okay, so we learnt about the identity matrix, which basically is this one matrix which has ones in the diagonal. And there's a very good reason why they run in the diagonal. Okay. That's an identity matrix for 3D. You should all know what it looks like for 2D. You should all be able to conceive what it looks like for 4D and 5D and 6D. Okay. We discussed the translation in a matrix, the fact that you can't do 2D translations in a 2D matrix. You have to put the translation at the end of the matrix, which makes it a weird shaped matrix. We looked at how you embed scale in a matrix, and basically they sit along the diagonals. We looked at the rotation in a 2D matrix. You should know this formula. So we have cosine A minus sine A, sine A, cosine A. Should be there in your memory, and if it's not, it should be there in your book. We looked at matrix multiplication in 2D. And it's hard, but I still expect you to do it. And let's open up the link, and I think you'll find that there's no internet connection. It's class. It's class. I can play dinosaurs. Oh, come on, give me an internet connection. Connect. Let's try that again. Come on, come on, come on, come on, come on, come on. Come on. Took me about 20 minutes to do this bloody animation, so... Okay, so I've done a little animation of how ABCD multiplies against PQRS. Because I'm hoping that maybe if it's animated, it'll work better. And I've even colour-coded it as well, and maybe that'll work better. Okay. Right. Okay, so you should know how to multiply two 2D matrices together. Check that you have 2 of every element. 2 A's, 2 B's, 2 C's, 2 D's, 2 P's, 2 R's, 2 Q's, 2 S's. If you've got 2 of everything, it should be about right. Okay. We also looked at why the hell we bother with matrices. So we had the object transform matrix. We had an idea that every object in the scene has a transform matrix associated with it, and what we could do with it was there was this thing called local space, where it doesn't do anything, and then there's this thing called world space, and what the transform matrix does is it takes those verts and it takes them out of local space and it puts them in the world space. And then we looked at what happens if you do the inverse of a transform, and basically that allows you to look at the scene through another object. So you can take another object in the scene, normally a camera or a player, and you can do the inverse transform from world space to its local space, which is usually a projection, and you end up with a 3D view with a bit of perspective. And we looked briefly at how that perspective was done. So that's where we're up to. Any questions? Sweet. Okay. Homogeneous coordinates. Right. There is a YouTube video from a GDC talk, which is how somebody else explains homogeneous coordinates. It's really good. There are lots of other people explaining homogeneous coordinates, and it's really difficult to understand. I don't know which one's the best for you, but I found this talk really, really easy to understand. I will attempt to explain the same thing. So we know that matrices are used to transform objects, right? We also can transform nodes and vertices. We can also transform directions. We can also transform other matrices. So matrices are basically just a big bunch of numbers, and they help us do transforms. In 3D graphics, how big is the matrix? Well, straight away we think it's 3D, so therefore we should have a 3D matrix. So we have our X and our Y and our Z. We can encode scale, and we can encode all of the rotations, but we cannot encode any of the translations. And that's because translations theoretically are in another dimension, so the next dimension up. So we need to encode the translations. So we need to put another row into our matrix. So now we can encode scale, all rotations and translations. So we're happy. Okay, so we now have 4 rows and 3 columns. Again, what is weird is there are no standards. So I've laid it out in what they call a row. You can also lay this out in columns and end up with a 4x3 matrix. Just to really kind of confuse things, again, there are no standards. So you can see this has got 3 elements, 3 columns, 4 rows. This has got 3 rows and 4 columns. Depending on the game engine and the programmer, they just pick randomly. Great. However, we're just worried about the principles, not the practicalities. So we have a 3x4 matrix, and this is not an augmented matrix. It's not square. And the problem with non-square matrices is we can't multiply them against each other. We can't multiply a 3x4 by a 3x4 because row columns need to match to do matrix multiplication. So what happens is that they agree that we need to make it a 4x4. So that means we need to, in my case, I'm going to stick another column on the end. So it's now a 4x4 matrix. Okay, and then if I stick another column on the end, the question is what do I make those values? Again, literally, I pluck them out my butt at this point and go, well, what's worked previously? 0, 0, 0, 1. So in other words, this is an identity matrix. That's okay. So we're all happy now. We have a 4x4 matrix which is capable of encoding rotation, of which there are 3, scale, of which there are 3, translations, of which there are 3. We can encode all of that in a matrix, and then we can multiply those matrices together. So are we good? No. Still, there's another problem. How do we multiply a vector 3, x, y, z, against a matrix 4? Okay, well, let's just add another column on. So to multiply a vector by a 4x4 matrix, we must have a 4D vector. So we get x, y, z, and w. Because there wasn't anything after z, and mathematicians don't plan ahead. So we now have a vector 4. Okay, we are now up to what is generally considered the consistent standard in all 3D graphics. So all of your points are actually four-dimensional points. They have an x, y, z, and they have this hidden w. All of your matrices are 4x4 matrices, right? Where the translation is in that matrix, because it could be in the last column or it could be in the last row, you need to figure out. We're not going to worry about the practicalities of that. You just need to understand that that's the issue. So now we have a w, and what is w? And w is the homogeneous coordinate. And that is like, okay, big whoop. So what is the homogeneous coordinate? What does it actually mean? What can we use it for? Because it solved a problem. In other words, our matrices can't be multiplied until we go through this big, long chain of events. Now we've got to the end of that chain of events. We ask ourselves, if mathematics has forced us to do this, there must be a reason for it.
Why do we need to multiply matrices together again?
Because if I'm in a tank, yeah?
Is that how you apply it, like a translation?
Yes.
Okay.
So when I inherit the movement of the tank, basically I multiply by its matrix. Right. So what does W actually do? It indicates whether or not you're talking about a direction or a position. And up to this point, we haven't worried about the difference between those two things. We've basically said that vectors are vectors, and we've basically said that points are points, and we've basically treated points as vectors and vectors as points completely interchangeably, because there isn't really any mathematical difference while we've been fiddling around in 2D. However, once the bright-eyed people worked out you need a 4x4 matrix, they worked out you need a W, then they investigated why you need the W. And the W tells us whether we're dealing with vectors or whether we're dealing with positions. So, and remember I was saying vectors there and points are places. There's a distinction between those things. Vectors are a translation. They go somewhere. Points are actually specific points and they don't go anywhere. So we indicate this by saying W0 is a vector or a direction. And it should not be translated. And W1 means it's a point or a position. And it should be translated. So in other words, we know if we've got a vector and we're doing matrix multiplication, we need to translate or not. If it's a vector direction, we don't need to translate it. If it's a point or position, it should be translated. In other words, points get moved by the transform, directions don't get moved by the transform. And this is a really, really important concept. And it's absolutely mind-blowing about why. It's amazing the maths actually works out. It's like somebody planned years in advance. So if we consider a vector 2D with a 2 and a 1, I hope you can all see, it doesn't matter where I put that vector, it's still a 2-1 vector. 2, 1, 2, 1, 2, 1, 2, 1 vector. And I can stick it anywhere I want it. Where it starts doesn't matter, it's still a consistent 2-1 vector. Okay. So, we know that I can move vectors around. That's a good thing. And the vector is still the same vector. Okay, so what about a position? Okay, there's one position. 2, 1. And that is it. Any other position is a different position. Okay, so there's only one position. And therefore, translation does make a difference. So, can we add vectors? Yes, we can add vectors. If I have a vector here, which is, I've got this first vector, B, which is 4 and a 1, and I've got another vector here, which is a 1 and a 2, and if I add them up, 4 and 1 is 5, 1 and 2 is actually equal, 3, So I end up here. So I add two vectors together, I get another vector. And if I add the w's up, 0 plus 0 is 0. So if I add vectors, and I'm using homogeneous coordinates, I still get a vector. That's nice. That's handy. That's pretty important. Okay, can we add a vector to a point? Okay, I have a point, I have a vector. If I add this vector to this point, I get this result. I get another point. And if I add my w's, you'll see that I'll add a 1 and a 0, and I'll end up with a 1. So a point plus a vector is a point. No questions yet. Okay. Can we subtract 2 points? Yes, we can. I've got a point A and I've got a point B, and when we subtract 2 points, we end up with a vector. Because if I subtract A from B, you can see that what I get is the difference between A and B. I get the axial difference. B, which is 5 minus 1, is going to be 4. And on the y-axis, we get 2 minus 1, which is 1. So we subtract 2 points, we get a vector. And again, in the w's, 1 minus 1 is 0. Can we subtract 2 vectors? Yep. I have a vector here, I have a vector here, I subtract them, I get another vector, and if I do the maths in the homogeneous coordinate, 0 minus 0 is 0. Okay. Hey?
This is what I've been waiting for. This is when it falls apart.
And this is where it falls apart. Well, this is where you think it's going to fall apart, but yeah, you know, the hero turns up at the last minute and saves the day. Can we add points? Okay, so if we add point A to point B, we get a result. We get another point. But is it meaningful? Pretty weird, and I'm not so sure it's useful. And what tells us that it's weird is that when we add the w's together, we get a 2. A W. And we're like, we've defined what 0 is and we've defined what 1 is. We haven't defined what 2 is. So we have an anomaly. We have a weirdness. So we have a 0. We know that 0 is a direction. We have a 1. We know 1 is a point. We have a 2. What is a 2? Okay, so we can say, okay, we don't know what a 2 is, but we want it to be a 1. Let's get it back. Let's try and get this back to a 1 by dividing by w. So we go x divided by w, y divided by w, z divided by w, w divided by w. 2 divided by 2 is 1. Again, these seem like very arbitrary rules. Somebody's just picking things out and just doing stuff with them. Why are they doing it? And because a lot of mathematicians just play with this stuff and then they make discoveries. Okay, so if I divide everything by w, now what do I get? I get an average. I get a point, which is the average position of those points. Which, again, when that happens for the first time, when you read this for the first time, you're like, that is really cool. That is so useful. So we can add points together. We end up with a weird homogeneous value, depending on the number of points we add. So we can add 1,000 points, we can add 100 points, we can add 2 points. Doesn't matter. that W will tell us the number of points we just added. And if we divide by W, we get an average. Okay, and dividing by W, does that seem a little bit like deja vu? Because a little while ago we looked at perspective. And we looked at perspective and we went, what we need to do to make something look like perspective is we need to divide by Z. And we realise that when we divide by Z, things that are far away get smaller. And that's kind of really handy that far away gets smaller when we divide by Z. All of these things that I've just done, they are on GeoGebra, so you can play around with them and actually prove the fact that I haven't been bullshitting the whole time and that maths does add up. I nearly did it. Go away. Thank you. Go away. Right. Okay. So, what we were doing last week, we have an object somewhere in space, and we have a screen, and we have our object in the scene. And our object in the scene, we know, is at local 0, 0. And then what we do is we imagine a virtual screen, which is always at Z1, because the maths is easy. Don't put it at Z pi, because the maths is weird and difficult. Put it at Z1. And if we put it at Z1, and we do this division by Z, we get a projection where this ray hits this plane, which is the screen. So, doesn't matter where this object is. We can move the object around, the projection is good. Can't see it. You can see it. Can't see it. You can see it. Okay. What these lines actually are is the projection of the homogeneous coordinate. So what the mathematicians have worked out is if we use something called the pure perspective projection, which you will come across quite often when you need to do weird stuff with what the viewer can view, especially something like clipping. We make this matrix, which is clearly not an identity matrix. You can see that it has X, Y, Z, it has all the ones. But then when we get to the end, it does something weird. And what it does is it takes the Z component and puts it into the W component. And then it ignores the W component, just throws it away. Because we want to make sure that we don't deal with the W. So, if we multiply our X, Y, Z by the pure perspective projection, we get X times 1 and everything else times W times 0. X times 1, Y is 0, Z 0, W 0, we get X. We do the same on the next row, we get Y times 1, we get Y out. We do the same on the next row, we get Z times 1, we get Z out. And we do the same on the last row, we get Z times 1, we get Z out. And you think, why do this? Seems like hard work. Because the graphics card's doing it for free, yeah?
On the third line, you have two ones.
Yes.
And why do you have only one Z on like on the bottom? Then you have multiply by 1. And then on the last line, you have again multiply by 1. Why is the W 0 on the third line?
Because it's 0, 0, 0, 0.
No, yeah,
which
but on
is this
on
row.
the third line you have 2 1s.
Yes, because that's 2 ones.
Why is there 0 then?
Because this is the matrix.
Oh.
We want to multiply X, Y, Z by this matrix. When we multiply X, Y, Z by this matrix, we get this. So you get 2 ones in the Z column, nothing in the W column. What you get out from that is X, Y, Z, Z.
I appreciate you not sticking to a standard even in your presentation.
I am sticking to the standard in my presentation because you remember it rotates.
Yeah, exactly. That's the point.
That's why I have to write it out. My notation is not the direct text notation because I grew up in OpenGL. It's hard. Trust me, it's hard. You're in for a world of pain over the next 2 years as you go in and out of OpenGL, Vulkan, PlayStation, ATI, NVIDIA. No freaking standards everywhere. Okay. We divide by W to return to point space. So, and we also know that W is Z because we've encoded W as Z. So what happens is we make a decision. Once we've gone through here, we divide by W. And what that means is effectively we divide X by Z, Y by Z, Z by 1, W by 1. All that to do a perspective transform. Seems complicated, but it's for free because your graphics card is busy spewing through these matrices. It's why you spent 300 quid on a graphics card so that it can just spew through matrices. That's what it does really, really fast. So this is how perspective is achieved on your graphics card. Basically, all of those objects get multiplied by a big long list of transforms, and then at the end of those transforms, it hits the pure projection, and then it hits a scaling projection. So basically, the pure projection will do a 90-degree camera, which is pretty ugly, but for some reason is standard these days. But if you want a telephoto lens, you know you need to tweak that Z value. And if you wanted a wide-angle lens, again, you would tweak the Z value. We're very familiar with changing the field of view in most games, and it's very easy to do. Are there any questions on the homogeneous coordinate? Because I'm amazed. Well, I'm not amazed. It took me about 3 weeks to just sit there and think through it.
So on the last thing at the bottom, I can't quite read that. Is that Y divided by Z, or is it Y times by Z?
It's y divided by Z. So the homogeneous coordinate is this extra W. It's used to encode whether or not we're dealing with positions or vectors. It seems very arbitrary that it's encoding this information, but the reason that it does encode that information is that it actually leads us to be able to do perspective projection. Yeah.
And it will just be 1 or 0.
So in the pure perspective projection, it will be set to 1 in the Z, and W will be set. All the W's are set to 0. So it's a good idea to make a note of the pure perspective projection. Yes.
I don't even know how to phrase the question. In the pure perspective projection, Z is okay, words. I need words. The 2 ones in the how do you the X value is obviously 1 at the top. Then Y is in the middle. Is your Z in there? Am I thinking of it wrong if I try and add them together and make it 2, or is it something else and I'm misunderstanding something fundamental? Like, what am I looking at when I'm looking at that matrix?
This matrix?
Yeah, it's a bit of a broad strokes question, but something about the rows and columns that I'm not 100% on.
Yeah, this matrix is weird.
Yeah.
Right? It's clearly not the identity matrix.
Yeah.
So we know an identity matrix would just be 1s in the diagonal,
Yeah.
and we know it wouldn't do anything. Right? Okay. So what this does is, first of all, the fact that it's got all 0s in the last row, and if you can imagine your X, Y, Z, W alongside of it, you can clearly see that what will happen is all those 0s will cancel out.
Yeah.
So W just gets wiped out.
So you just times it by a 1/4 matrix of just naming X, Y, Z, W. That's all. How that works.
Yes. So we're rotating, we're multiplying this against a vector, X, Y, Z, W. And then we need to know what happens to that vector when we multiply it by X, Y, Z, W. And what happens to it is that what spews out the other end is X, Y, Z, Z. So W gets replaced by the Z. And we know that this is the case because this is X. X times 1 gives us X. This is Y. Y times 1 gives us Y. This is Z. Z times 1 gives us Z. And then Z times 1 again gives us another Z. And then, of course, the last row does bugger all because it's all zeros. So what this does is it converts our X, Y, Z, W into X, Y, Z, Z. And again, it looks weird that we've gone to all this effort to do that because you'd think, I could write that really easy in code. Why do I go through a matrix to do it? And that's because it's done on the GPU, not on the CPU. The GPUs are already set up for this. So, we get an X, Y, Z, W. Then we say to the graphics card, do the divide by W. And W is encoded to be Z, so therefore it's divided by Z. So our Z value gets chucked into the W, then it does a divide by W, which means that what we get out the other end is X divided by Z, Y divided by Z, Z divided by 1, W divided by 1. What spews out is a pure projection. Okay. I will quickly rally through the dot product and the cross product. Okay, so far we've been adding and subtracting vectors. We can also multiply vectors. There are two ways of multiplying a vector. One is called a dot product, one is called a cross product. The dot product is also known as the scalar product because the thing that it chucks out the other end is a single number. And the cross product is also known as the vector product because the thing it chucks out the other end is a vector. So one of them chucks out a number, one of them chucks out a vector. The dot product chucks out a number. Here I have two vectors. And you'll get to play with this afternoon. Well, some of you will. And I'm going to move this vector around. Let's just zoomy a bit. Right, if I move this, you can see that the dot product changes. No surprising. Does seem a bit arbitrary though. Big numbers, what do they actually mean? So the important thing that you can take from this is that whilst these two vectors are heading in the same kind of direction, the number is positive. And when these two vectors are in opposing directions, you can see that the number is negative. And trust me, because I'm not going to be able to do it live, when the dot product is 0, it's because the two vectors are perpendicular. That is, they're at right angles to each other. How is this particularly useful? Because that's a pretty big number and it doesn't really mean a great deal. So let me just show you and I have no right mouse button. go back round here. Let's see what happens when I just move along perpendicular to that green vector. You can clearly see the dot value changing. So the output from this, the dot product, changes. And if I go and move it up and down, the dot value doesn't change at all. So this means that this dot value is somehow proportionate to where this vector intersects this vector at 90 degrees. And this is called a projection. In other words, if this vector had a light shining down and it shone down onto this vector, you can see I've got a little blue line. That line always touches that vector at 90 degrees. This is proportionate to the dot. And I can divide my dot by either of the magnitudes of the vector and get another number. And you just think, okay, so what is the purpose? What are we gaining from this? Why bother? So, come on, zoom. Let's just be clear about a couple of points. First of all, it doesn't matter where in 3D space I put these vectors. Let me just chuck them around a bit. Wherever these vectors are in 3D space, there should be a way in which, one, that these two vectors can line up flat, and two, that there will always be a way that I can draw a line between the two vectors that will be 90 degrees absolutely guaranteed. So, given the fact that I am moving this vector, and let me switch it to local. Third one's a charm. Local. Again, whenever I am going to move this along its local space, zoom out. There we go. Thank you. So I can move these vectors around. Wherever I choose to position these vectors, I should be able to create a line that runs between them that is the projection from one to another, and that should be 90 degrees. And I should be able to move this vector. And again, it can be either one of them along this perpendicular. And when I move it along this perpendicular, you can see my dot product doesn't change. When I move it along the opposite perpendicular, which is this axis, it will change. So what I'm going to do is I'm going to put this, in fact I'm just going to reload it because that'll be quicker. Does this remind you of anything? If I move this, it changes. And if I move this, it does not change. Does this association remind you of anything you've seen in the past?
The trig circles.
So what does it remind you of?
The circles. Trig. All right. What
So it reminds you of the unit vector.
yeah.
Am I right?
It was a circle we were using trick, okay? Come on, leave me alone. I know what I meant.
When I moved this point, this is our dx. This is our dy. This is our angle, and there's a relationship between the cosine of the angle and the length of that vector. So in other words, there's a relationship between the dot product and this length. Okay, so if there's a relationship between the dot product and this length, which at the moment is very arbitrary because it depends how big these vectors are, you suddenly go, so what if these vectors weren't big? What if these vectors were 1? Both of them a normalized unit vector. Then what do you think would happen? What do you think the dot product would be? The dot product of two unit vectors will be... Oh, come on, someone please tell me. What does this remind you of? There's the unit dot product, right? I'm moving the vectors around. What does this unit vector dot product look like? It's one of those. Which one is it? It is cosine. Yes. So, the magic of the dot product is if you have unit vectors, which is very common in computer graphics, and sometimes you just got to force them to be unit vectors. If you have two unit vectors and you take the dot product, you get the cosine of the angle between them. And I'm sure you can all visualize that it doesn't matter where those two vectors are in space, in 3D space, there will be a point where there is an angle between them. The exception will be parallel lines, because they are just messing you up. So you can understand the dot product will always give you a cosine of the angle. So when they are collinear, as we like to call it, that is when they are together, you will get a 1. When they are perpendicular, you will get a 0. When they are opposed, you will get a -1. That is really useful. Trust me, dot products get used a lot in video games. A lot. Right, so we can understand the dot product has 3 significant states. So if we just take two vectors, we get a less than 0 state, a 0 state, and a greater than 0 state. These states occur depending, I ain't going for a while. We've got cross product yet as well. Right, so we understand that there are 3 states. We can also understand that if we make these unit vectors, then that the dot product is the cosine of the angle between those two vectors. And that is really, really useful. You want to calculate where somebody's heading, or where somebody's facing, or if something's behind you, vector maths, dot products. Okay, so what you take from this is, again, the dot product of 2 unit vectors, cosine of the angle between those vectors. Dot product of 1 when the vectors are the same heading, between 0 and 1 when the two vectors are acute, 0 when the two vectors are perpendicular, -1, well, between -1 and 0 when the two vectors are obtuse, and 1 when the two vectors are opposed. That should be -1. I did that. Okay, and just to finish off, cross product. So that's the scalar vector. That is dot product. We need a cross product as well. This is the cross product. You take two vectors. Any two vectors will define a plane, and any two vectors can have a vector perpendicular to those two vectors. So here we have two vectors. Let's not worry about the order just yet. So if I move this around, you will see that I can move this vector. It changes the length of the cross product this vector will always be perpendicular to the other two vectors. So what is the point of that? We can multiply two vectors together, we get a third vector that basically sticks up between them. What it does is it defines a plane. So, I'm sure, again, you can all visualize and understand that I have here a plane in 3D. Wherever I go and move these vectors around, I will always be able to form a plane. And the blue vector points in the direction of the plane. So it is normal to the plane. And by normal we mean it is at 90 degrees to the plane. So we can see that I have a plane and that blue vector will always be sticking up 90 degrees to that plane.
Wouldn't it be pointing away from it? Does it spawn at the plane and it goes away from it?
Yeah. Yeah. So this blue vector is called the normal and it points away from the plane. And it is defined by the cross product of those two vectors. So this is how we can define a plane. Now, we can define a plane with two vectors, and also we can define a plane with one vector and its displacement. Okay, but there is another very interesting property about this, is that if I look around this plane, you can see that, okay, when the vector is pointing towards me, the plane will be drawn. It's not a very good display, but trust me. That plane will be drawn. If I go around the back of this plane, it disappears. This plane only has one side. And that is very common in computer graphics, except on the PlayStation 2. This is called backface culling. Triangles are only drawn in one direction. So you have to ask yourself, how does it know whether a triangle is to be drawn or not? And that is the order of the vertices. Again, there's no standards. Could be clockwise, could be anti-clockwise. So if I go and have a look at this point here, and you can see that if I start red, green, blue, you can see that what I'm doing is I'm going around in a clockwise order, which is indicated by the fact that this thing is red. And if I go and move my point and cross the green line, you can see that the plane will flip. And I will see, look, I'm looking at the other side. And if you look at our order of red, green, blue, it's reversed. It's now anti-clockwise. So, Cross product gives us access to the plane equation. Cross product defines a normal to a surface, which we need for lighting. Cross product also defines whether or not we draw or not draw triangles. Because for most 3D graphics, we backface color, which means if you're looking at this computer, I'm looking at the screen and I need to have it drawn. But for the rest of you, you can't see this screen. It's facing away from you. So I can save a lot of processing power by backface culling. And normally, for most geometry that is not environmental geometry, backface culling saves half your geometry, roughly. Okay. Well done for surviving that. That's cross product, that's dot product. Bring questions to me on the Wednesday. I have booked